Good afternoon, everyone. Welcome to online classes on digital electronics. Right, the subject we are going to discuss is digital electronics, easy and logical subject, which is having very good weightage in GATE and ESC, which can decide our life as well as future also. And the weightage for the subject for different branches and different exams. For ECE, we have been getting around 10 marks in GATE exam, around 30 to 40 marks in ESC objective, and more than 40 marks in conventional. Similarly, for electrical GATE exam, on an average, we are getting around 5 to 6 marks. For ESC, we have been getting around 20 marks in objective, as well as conventional, around 20 to 30 marks. And coming to instrumentation GATE exam, on an average, 8 marks we have been getting from digital electronics. That is weightage of the subject in GATE and ESC. The screen is black. People are worrying about screen. I haven't written anything. Until that, please wait. Don't be in hurry. Screen is black. I didn't write anything. Please wait. Just I'm addressing this meeting, right? And for your queries, I'll answer at the end. Don't raise the hands in between. I'll give you time. Every question will be cleared, as it is a online platform. You should have some patience. Please wait for your turn to ask doubts. I'll clear all those doubts. Don't be in a hurry. Right? Now, after understanding the weightage of the subject in GATE and ERC, now let us see what are the topics we are going to discuss in digital electronics with respect to GATE and ERC. At what level we need to study, what are the topics we need to concentrate, what type of questions we have been getting. Let us get that clarity, then we proceed to discuss each and every topic in detail. Here we start with number systems. The first topic we start with number systems. What do we study in this number systems is basics of number systems. What is the terminology of a number system? Like base or radix, weight, weighted value. What is that radix point? After understanding basics of number systems, then a quick review we do on base conversions, one number system to another number systems, how to convert. If there are any easy methods, what are the methods we have? to convert from one number system to another number system, sir? What type of questions we can get from number systems? With this, basics of number systems will be completed. Then, the most important area from number system basics is by giving an equation, they have been asking what is the possible base values which can satisfy given equation. They may giving one equation, they may be giving multiple equations. You need to calculate the base values which can satisfy this given equations. Then how to solve such questions? One easy method is if it is a multiple choice question, we can verify with the options. If it is numerical answer question, you need to mention what is the base value. In such cases, how can we answer these questions? We need to understand. So, second type of questions is by giving an equation or multiple equations, they are asking you to find base of the number systems in which these equations are valid. Then, after understanding this, next is complements. What is complements of a number system or complements of a number? What are the complements we have? You might be knowing already 2's complements and 1's complements of binary number system. Similarly, 10's complements and 9's complements of decimal number system. 8's complements and 7's complements of octal number system. 16's complements and 15's complements of hexadecimal number system. Or in general, we can say radix complements and diminished radix complements. Depending on number systems, we are getting two complements. One is radix complement, second one is diminished radix complements. Then how to get these complements? Are there any easy methods to get complements or to write complements easily? That's what we are going to observe in this. After understanding complements, the most important concept from number systems itself for all the competitive exams is signed number representation in binary. Frequently, we have been getting questions from this area. So remaining areas, bit methods you may be following, but you need to understand in depth about signed number representation in binary. When we have both the positive as well as negative numbers, to differentiate positive and negative numbers, we are using plus and minus symbols for our convenience to differentiate positive and negative numbers. But digital system cannot accept other than ones and zeros. Digital system can accept only ones and zeros. To differentiate positive and negative numbers, if I am using plus and minus symbols for understanding myself, but digital system cannot understand these plus and minus signals or symbols. Using ones and zeros only, you must be in a position to differentiate positive as well as negative numbers. With predefined protocols, we have three representation for these signed numbers in binary. One is signed magnitude, one's complement, and two's complement. Total three complements we have, or three representations we have. Right. Let me check. Is it visible my screen now? Ankur Kashyap. People are saying yes, you only saying that no. Is there any problem in your system? Yes. Now, Yes, that's what I have written. Dinesh sir. Nothing I have written. Yes, yes. Please stop responding. Yes, visible. I understood that. Yes. How about voice? People are saying audible. Okay. Many are saying audible, clear. These are the answers I'm getting. Please check if there is any problem. Okay. Thank you for your response. Yeah, Dinesh Roy, I have written just number systems. Just have written number systems. Right. So I was talking about a signed number representation in binary. We have three representations for signed numbers. One is signed magnitude, one's complement, and two's complement representations. What are the rules of each and every representation? And what is the range of n bits of each and every representation? Then, which one is preferable among three representations and why? These are the important things we need to understand. Rules behind each and every representation, range of n bits in each and every representation, what is the minimum number of bits required to represent a number, how to calculate that. Then among three representation, which one is preferable for our digital circuit design or digital system design? Why? These are important things we need to focus from signed number representation binary. Then next, subtraction using complements. How to subtract one number from another number without using subtractor circuit? Using complements. Subtraction using complements. When we are using complements methods, we can subtract one number from another number without using separate subtractor circuit, using only adder circuit. What are the circuit or what is the method of subtraction in this? One is R's complement method, other one is again R minus 1's complement method. Radix complements, diminished radix complements. We have two methods for subtraction. For respect to number systems, we have two methods. So using these methods, how can we avoid designing subtractor circuit separately to complete subtraction using adder circuits? That's what we are going to study in this subtraction using complements. These are important areas where we need to focus for our competitive exams. We have codes B, C, D, XS3 and different codes, gray codes. Properties of these codes and code conversion circuit I'm going to discuss in combinational circuits. Let me mention once again, codes and code properties and code conversion circuit design. All these I'm going to cover in combinational circuit. Until that, please wait. Don't be in hurry to learn now itself in number systems. Codes and code properties separately I'm going to discuss in combinational circuit, because there we are going to design code conversion circuit. Instead of discussing properties here, they're designing circuit. I want to cover these concepts in combinational circuits only. Don't be in hurry by going through some questions. Right? You may be getting doubt. Oh, codes. Yes, codes will be covered in combinational circuit. Until that, please hold on. That is the introduction about number systems. First topic we are going to see. The next topic is Boolean algebra and logic gates. In digital circuits, the second topic we are going to cover is Boolean algebra and logic gates. Right? In chapters we say this is only one chapter, but while discussing, first we discuss Boolean basics, then we are going to see logic gate basics. What we are going to study in Boolean algebra? Boolean basics, Boolean principles based on switching theory. Where we started our digital circuit principles, from there we are going to start switching theory, principles of switching theory, then basic functions of digital circuit design. Those are AND or inverter. Then based on these rules, based on these three functions AND or inverter functions, it is proposed a set of rules for digital circuit design, which we name it as a Boolean rules or Boolean axioms or Boolean postulates. Based on three functions AND or inverter, it is proposed a set of rules for digital circuit design. Those rules are named as Boolean rules or Boolean axioms or Boolean postulates. Then terminology of Boolean function, like writing expression in SOP. What is SOP? Writing expression in POS. What is POS? And most importantly, min terms, max terms. And what is the relation between SOP and POS? Relation between SOP and POS, we expect Vijay Kumar Reddy. I'll use a screen. I'm going to write. I hope you are able to see number systems and Boolean algebra. Just I'm introducing topic. Have some patience. Right. Ashish Kumar. Yes, I'll introduce myself. Please wait. Yeah. Ganesha, I'll do. For you, I'll do. Wait. For now, I have only this one. I'm continuing with this. Yes, I try to do that. Right? Ganesh. Right? Kashyap. Everyone is able to hear. Is it audible? Vinay. That's not in our hands, sir. Please. Yes. If you keep on messaging, right, it may be, right, interrupting the regular flow. I will take necessary actions to give my best. Online platform also, I'll try. Yes, Gopal Krishna, I'll show you that. Wait. Right. Right. I introduced two terms. One is SOP and POS. Most of you may be knowing that SOP, sum of products, we are writing using min terms of a function. By using min terms, we are writing SOP, the input combinations for which Arpit Anand, for all that queries, I'll give you time. Please don't disturb the class. Otherwise, give me that indication, whatever is there on Q&A, neglect. When I'm observing, so there are some messages, then I may be thinking that there may be an issue with video or audio. That is the reason I've been checking every question or every query. Please don't give me that indication, right? There will be unnecessary messages also. I don't have that opinion, but don't give me that opinion. Please, all your doubts will be cleared. At the end, I'll wait for how much time you need. That much time I'll wait. I'll clear each and every doubt you have. I'll give you chance to interact. There will be there. Yes, yes, I do that. That's what I've been saying. At the end, in the break time, I utilize that time effectively to answer your doubts or questions or whatever you have, right? For that, I'll answer, right? We allocate a separate time in every session for your doubts, right? I'll clear each and every doubt, each and every simple doubt, each and every, right, subject doubt, each and every personal doubts, right? If you have any personal doubts, like what to prepare and how to prepare, all those, I'll answer each and every your doubt. Please wait. Please don't interrupt me with your doubts now until unless you have any problem with audio or video. Please don't message me, right? If I ask any question, they try to answer. Until that, please don't interrupt me. Don't interrupt the class. You have been interrupting not only me, it's almost 200 plus students. So it's a valuable time of everyone. I hope you are understanding this in a positive way. Right? Fine. Right. Let me introduce the topics. Then we will enjoy each and every, right, corner of the subject, each and every topic. Right? Okay. So what I've been introducing is about Boolean algebra. I discussed what is the terminology we need to learn in the number, right, in Boolean algebra. Then I have asked a question. What is the relation between SOP and POS? SOP is written using ones, which are min terms. POS is written using zeros, which are max terms. That we know already. While writing the product of sums, we are using zeros, which are max terms. While writing SOP, we are using min terms. Then what can be the relation between SOP and POS? Generally, we think that it is SOP is complement of POS. It is a wrong perception. It is a wrong perception. I'm going to give you clarity. No need to worry about the statements. So we need to understand this correctly. Otherwise, we are going to face some problems at the next levels in combination as well as sequential. So we need to understand these concepts correctly. The relation between SOP and POS. What is the relation? I'll introduce later. Until that, hold on. Generally, we expect that it is a complement. One is complement of another one is a wrong perception. Why we are getting the perception also we see. We discuss that in detail. Until that, hold on. And after that, we need to understand about dual complement of a function. To get complement of a function, we are using De Morgan's principle. For using De Morgan's principle, we must know dual of a function. What is dual of a function? How to get dual of a function and how to get complement of a function using De Morgan's principle. So what we are studying in Boolean algebra is a terminology, min term, max term, SOP, POS, canonical or standard SOP, canonical or standard POS, relation between SOP and POS. Then how to write dual of a function, how to get a complement of a function using De Morgan's principle. Right? So we have some more advanced concepts of Boolean algebra, like what is the maximum number of functions possible? What is the maximum number of self-dual functions possible of n variable functions? What is the maximum number of self-complementary functions? All these I'm going to address in detail. Advanced topics of Boolean algebra. Number of functions, number of self-dual functions, number of complementary functions. Instead of just remembering the answer, how we can analyze this also, I'm going to explain in detail. With that, we are going to wind up Boolean algebra, and the next immediate topic, it is related to Boolean algebra only. We are going to study logic gates. What we are going to study in this logic gates? Functionality of each and every logic gate. What is speciality of each and every logic gate? What are the basic gates? What are the universal gates? What are the derived gates? And or inverter basic gates. Then we have a speciality of NAND NOR. We are going to cover that. We have a speciality of XOR and XNOR. What is the use of XOR and XNOR? Where can we use that? XOR and XNOR. Properties of these logic gates. Implementations of logic functions using basic gates. Implementations of logic functions using universal gates. Then a most important topic from entire digital circuits is a propagation delay. Sachin, wait. Right. Don't raise the hands now. I'll give you chance to ask your doubts and I'll clear. Sachin Ninganur. Right? Wait. So, what is this propagation delay? Why I'm saying this propagation delay is important? Every year, compulsory one question on propagation delay. Directly in logic gate circuits, they may be asking propagation delay. They may be asking propagation delay in combination circuits like adders and different adders. And what is that worst case propagation delay? What can be the best case propagation delay of each and every adder? Which one is faster? Which one is slower? Different adders. Then by giving a combination circuit, they are asking what is the maximum time required to stabilize all the outputs from the point input supplied. Not only this, in sequential circuits also we are going to do propagation delay analysis by calculating minimum clock period. What we do here? Minimum clock period, T minimum. We are calculating maximum frequency of sequential circuits. Here also, propagation delay analysis only we are doing to calculate a minimum clock period. By calculating minimum clock period, we are going to analyze maximum clock frequency of synchronous counters as well as asynchronous counters also. Not only this, coming to converters, analog to digital, digital to analog converter, there by fixing that conversion time for one sample, we are going to decide what is the minimum sampling period we need to provide, what is the maximum sampling frequency allowed. Here also propagation delay analysis only. In converters, analog to digital and digital to analog converters also, we are going to do propagation delay analysis. Not only this, while coming to logic families, there also we are using propagation delay analysis. So which one is fastest? Which one is slowest logic family? Why CMOS logic family is slower? And what are the other advantages of CMOS logic family? All these things we are going to analyze with respect to propagation delay only. Once again, coming to memories, there also we are going to discuss about what is that accessing time, what is that operation time, and SRAM is faster than DRAM. Why SRAM is faster than DRAM? All these again with respect to propagation delay. Somewhere they have been asking question every year on propagation delay. That is the reason I mentioned the most important area from the digital circuits. I can say compulsory question every year from propagation. It may be in logic gate level, it may be in combination circuit level, it may be in sequential, it may be any other topic. Everywhere we are talking about speed of operation. So even though we are using 2 gigahertz mobile, we are looking for higher frequency. What is the reason? You want to use a high speed systems. Even though we have been upgrading with speed, we were using that 1 gigahertz processor. Nowadays we have been using that more than 2 gigahertz processor in our mobile. Still we are looking for right high frequency devices. As there is a demand for high frequency systems, people have been focusing on reducing propagation delay. So here in the basic level, I'm going to talk about propagation delay. What is the reason for propagation delay in logic gate? How is it possible to minimize that? What is the propagation delay effects in logic circuits? What are these unwanted glitches in logic circuits? How to eliminate these unwanted glitches? All these I'm going to talk in detail in logic gates and propagation delay analysis based on logic circuits. So with that, the second chapter will be completed, logic gates. Then next is K-map. Here we are going to study corner map. Corner map for Boolean minimization. And what is speciality of corner map? What is the basic rules of K-map minimization? Then terminology of minimization like prime implicants, essential prime implicants, redundant terms, selective prime implicants, minimal expressions if possible. When do we get multiple minimal expressions? What is the reason behind this? When should we consider other possibilities also for minimal expression? That is nothing but multiple minimal expressions. Using min terms, finding minimal expression in SOP. Using max terms, finding minimal expression in POS. Then One more important area in K-map is don't care. Generally, we have an opinion about don't care. What is don't care? 0 or 1. The opinion is because of the way we are utilizing don't cares. But in reality, what is don't care? Why we are getting don't cares? What is the reason behind getting these don't cares? Need to be understood. Why I am stressing this much here is about this point. In a function expression, if it is provided which combinations are don't cares, then we can utilize don't cares that we know already. That was sufficient for regular exams. But coming to competitive exams, how they have been framing questions is they don't mention which combinations are don't cares. Indirectly, they are specifying functionality of system. When they are specifying functionality of system, they are leaving some combinations which are leading to don't cares. But when can we consider these are don't cares? That condition must be understood correctly. For this, we should know concept behind don't care. What is don't care? Why we are getting don't care? When can we utilize don't cares? When can we neglect the don't cares? These are the important things we need to focus for competitive exams. Once again about don't care, what we need to observe, what we need to understand is why we are getting don't cares, why it is named as don't cares, how to utilize don't cares. These three things are important. Third one is very familiar for us. Am I right? So how to utilize don't cares, you might have done in your graduation also. But you might have gotten some doubts, but you have suppressed your doubts. Wherever you are getting those doubts, there only they are framing questions. If you are 50%, there is a possibility for doing mistakes. That is the reason let us become 100% in each and every topic. What I mentioned, what is the reason for don't cares? Why it is named as don't cares? If you are understanding these two, third one is very easy. How to utilize don't cares? Instead of following some rules which are specified, you can set the rules now because you are understanding the concept. Once you are understanding the concept, no need to follow anyone's rules. Or I say, no need to follow anyone's shortcuts also. So if I prepare a shortcut, if I make a shortcut, the reason behind that is I have done this concept, I have understood this concept multiple times. That is the reason I can frame a shortcut. And I know where that shortcut is failing also. As I framed a shortcut, I only know that where it is failing also. Blindly, if you are following shortcuts, obviously there may be possibility for doing mistakes if I'm not addressing where it is failing. So nowadays, questions are a bit different. Wherever there is a possibility for doing mistakes, with some assumptions, with some shortcuts, they're framing the questions. That is the reason in these years, concepts is important and learn the shortcuts also. But if you are understanding concept where the shortcut is also failing, we can understand. So conceptually, we can save time with the shortcuts. So concept is important. Shortcut also helping us in saving time, but we should not do a mistake where there is a negative mark. So you must be 100% in the concepts. That is the reason about don't care. Generally, we neglect the don't care. Don't care. No. Don't care is very important area. So in combination circuit also we are going to use don't care. In sequential circuits also we are going to use don't care. When can I use don't care? When I cannot use don't care? These things also you need to understand. So everywhere we are utilizing the don't care in combination as well as sequential. To understand why we are using don't cares there, you need to understand concepts clearly here in K-map itself. So what we are going to do, K-map, finding minimal expression in SOP, minimal expression in POS, then utilization of don't cares or minimization in presence of don't cares with concepts. So with this, we can say basics of digital circuits will be completed. Basics of digital circuits will be completed. And typically we have been getting 2 or 3 questions from these areas most of the times. 2 or 3 questions from these areas. So we need to understand these basics to understand digital circuit design, as well as it is giving score also, right, around 3 or 4 marks we have been getting from these basics. Then now we are ready to design digital circuits. In that, first one is a combinational circuits. Combinational circuits. What we are studying in this combinational circuits? First, we start with the 1-bit adder, 1-bit subtractor, then n-bit adder, n-bit subtractor, 1-bit comparator, n-bit comparator. Then converting from one code to another code, code conversion circuits. Then important areas, MSI devices. You should understand what is this MSI. Medium scale integrated circuits. Few of the logic gates are integrated, manufactured for a specific function. Which are those? Multiplexer, demultiplexer, decoder, encoder, priority encoder. These are the devices, MSI devices we need to understand. Multiplexer, demultiplexer, decoder, encoder, priority encoder. In this functionality of each and every device, constructing from lower order to higher order or higher order to lower order, implementing a logic function using these devices, specific functionality of each and every device, applications of each and every device, we need to understand. There we can wind up a combinational circuits. Next, sequential circuits. Highest weightage and different questions we have been getting. Sequential circuits. Till combinational circuit, with my experience, what I observed is most of the students are familiar. Coming to sequential, what generally we know is flip-flops, synchronous counter, asynchronous counters. With one example or multiple examples. SR, JK, T and D. Flip-flops, designing synchronous counter, analyzing synchronous counter, asynchronous counters, designing as well as analysis. That's it. But what else is required to know for competitive exams? What is memory element? What is basics of memory element? What is that NOR-based memory element, NAND-based memory element? Then what is a latch? Then what is a flip-flop? What is the difference between latch and flip-flop? Why can't we use latches in our digital circuits? Why flip-flops are preferable in our sequential circuits? What are the problems in latches? How those are rectified in flip-flop? What is the major difference between latch and flip-flop? Then what is race around? What is the reasons for race around? How to eliminate race around? These are basics of sequential circuit. Then we can get into synchronous counter design, synchronous counter analysis, asynchronous counter design, asynchronous counter analysis. Calculating minimum clock period of synchronous counter, maximum frequency. Calculating minimum clock period, maximum frequency of asynchronous also. Then FSM, finite state machines, Mealy FSM, Moore FSM. What is the FSM need? What is the need of FSM? How these are helpful in designing a system for a specific functionality? With examples we are going to do. Then most important area from this is a sequence detector. What is the minimum number of states required to design a sequence detector? What is the minimum number of flip-flops required to design that system? And what is that optimization of number of states? What are different methods we have for designing or optimizing number of states as well as number of flip-flops required to design the system? This is what we have in our syllabus. You can go through recent years questions, especially EC paper. there was a question to calculate a number of clock cycles. So generally counters means what we think, present state, present input, next state, or present state, next state, what is the flip-flop inputs? These are two methods which we use in counter design as well as counter analysis. But the analysis is very different with respect to clock cycle. That is the reason always I say we should run our mind with clock about a sequential circuits. Every time while analyzing sequential circuits, if you are using clock, with respect to clock, if you are understanding flip-flop functionality as well as counter functionality, then you will be in a position to answer those type of questions. If anyone has attended my classes, always I play with clock to understand counter analysis as well as minimum clock period calculation with the clock cycles only. So every time I use clock, so I've been saying that the questions will be different. The questions will be different every year. Year to year, the level of questions has been changing. Try to understand digital circuits in detail. Very easy subject, very logical subject. If you're not understanding concepts and logic behind this, there is a possibility for doing mistakes, or you may be blank in understanding question itself. That is the reason I say easy when you're understanding concepts in detail, in depth. For that, we should spend 100% presence in the class, even though it is online. Try to gain energy as well as enthusiasm in learning the concepts. Physically, we may not be in the class, but virtually we are in the class. We need to focus, and I'm not there to motivate you every time. So you cannot expect a motivation to gain your attention in the class, because I am not able to observe whether you are listening or whether you are looking at a screen or not. I cannot observe. So you need to decide yourself whether we need to get benefits of this coaching or not. So already done, right? So we cannot change that because of this pandemic. Again, we pushed into the online classes. Utilize this in a right way. Let us understand concepts correctly to gain better ranks in coming GATE and ESC. I hope everyone understood my words in a positive way. Always my intention is to give interest in learning the subject. Do you find any problem in my audio and video? Please respond. Am I audible? Sachin Kashyap. What happened, Sachin? Are you there, Sachin? You can talk. I have enabled. Kashyap. Mangesh.
Hello, sir.
Sir, the voice is low, sir.
Yes, Mangesh.
Sir, the voice is bit low, sir.
Are you saying anything?
Yes, sir, the voice is low, sir, low.
Right. Just a minute. Okay. I'm assuming it is audible and video is also clear. I think no issues, sir. Right. That's what about sequential circuits we need to learn. Basics of sequential elements, latch and flip-flop, then race arounds, and conditions for getting into race around, elimination of race around, then synchronous counter design, synchronous counter analysis, asynchronous counter design, asynchronous counter analysis. Similarly, calculating maximum frequencies of these counters, then FSM, Mealy, Murray, then state minimization. These are the things we need to understand from sequential circuits. The next one is a common topic for all A to D and D to A, analog to digital and digital to analog converters. Basics of conversions, like what is that step size, how to calculate step size, what is the resolution, how to calculate resolutions, what is the formulas of resolutions, then different types of converters from analog to digital and as well as digital to analog converters. With respect to speed and complexity, we are comparing all these. Then, which one is preferable with respect to speed? Which one is preferable with respect to complexity? Which one is preferable with respect to these two? Then, sample and hold circuit. What is the need of sample and hold circuit? What is the basic parameters of sample and hold circuits? And how to analyze this sample and hold circuit? What are the parameters we need to understand about sample and hold circuits? That's what we are going to study in converters. Basics of conversion, like step size, resolution. What is it? Sampling duration. Then what are the different types of converters we have? Analog to digital as well as digital to analog converters. Then sample and hold circuits. Parameters of sample and hold circuit we are going to study. Like droop rate. All these we are going to study about sample and hold circuit. Then the next topic is logic families. Right. In this, mainly we focus on CMOS. Nowadays, only CMOS they have been focusing. We see comparison of logic families. What is bipolar and unipolar logic families? Right. Why we prefer unipolar nowadays? Why CMOS is very important or very popular nowadays? And what is the pull-up network and pull-down networks? Why pull-up network is constructed using P-channel MOSFETs? Why pull-down network is constructed using N-channel MOSFETs? Then how to construct a logic circuit using complementary CMOS? That's what we are going to study in this logic families. So comparison of different logic families and comparing bipolar and unipolar. In unipolar, why CMOS is preferable and what is that CMOS construction and how to construct a logic function using this complementary CMOS. Then next is semiconductor memories. What we study in the semiconductor memories? ROM, RAM. In ROM again, PROM, right? Erasable, PROM, EPROM. In that erasable, once again, electrically erasable and UV erasable. Then coming to RAM, SRAM and DRAM. What is the advantage of SRAM? What is the advantage of DRAM? Which one is preferable and which conditions? Why SRAM is faster than DRAM and why where we prefer DRAM and what is that volatile and non-volatile memories? What is that flash memory and why it is named as flash memory? That's what we are going to study in semiconductor memories. What is that here? ROM, RAM. In ROM, we are going to study that again PROM, EPROM. EPROM again electrically erasable programmable read-only memory and UV erasable programmable read-only memory. Then coming to RAM, SRAM and DRAM, we are going to study in detail read-write operations of this RAM and what is that ROM, read-only memory, where do we use ROM, where do we use RAM, and what is that volatile and non-volatile, comparing all these we need to do, right? That is semiconductor memories. With respect to electrical, till this we have syllabus up to converters, common for all the branches. And remaining like instrumentation and EC, they have remaining 2 topics. For electrical, first topics, right? Last 2 topics for EC and IN. This is a syllabus which we are going to cover, right? Now, right. EC total syllabus, whatever is there on the board, everything is there for EC. For electrical up to converters. For EE up to converters. These 2 topics for EC and IN. For IES electrical also, same syllabus. Right? For ESC also, for IES also, electrical, same syllabus. Right? Is that fine? Right. Now, let us get into first topic, number systems. Right. The number I have written on screen is a okay. Many are curious about other things other than subject. Yes, myself, I'm Pawan Reddy, completed MTech in VLSI design from NIT Karnataka. Work for TI Bangalore, work for service-based companies in VLSI area. I've been working with ASA from last 8 years. This is 9th year I'm entering. I've been teaching for GATE and ESC from last 13 years. I've been teaching for GATE and ESC. That's all about me. Nothing great, right? Now, the number I have written on the screen is 4,869. 4,869. You may be pronouncing like this. When can we say it is 4,000? 4 must be multiplied with 1000, which is 10 power 3. 4,000. That means 4 is multiplied with 1000, then only it is 4,000. 800, 8 is multiplied with 100, which is 10 power 2. 60, when 6 is multiplied with 10 power 1, 9, which is 10 power 0. 4,869. 4,000, that means 4 must be multiplied with 1000, then only is 4,000. 800, 8 must be multiplied with 100. 6 must be multiplied with 10, then only it is 60, and 9 must be multiplied with 1, which is 10 power 0. Then only it is 4,869. So why are you multiplying with 10 powers here? Assuming the number is in decimal. Then only I can pronounce it as 4,869. If I say the same number is in hexadecimal number, I cannot say 4,000. 4 into 16 power 3. 16 power 3 is not 1,000. Unfortunate thing, you might have done this also in your microprocessor analysis. Right? Move immediately A comma 4 3 instead of 4 3. What you might have said 43 hexa. Unfortunately, you might have said it like this. What is it here? Move immediately A comma 43 hexa. While saying that, you need to understand correctly. 43 you are saying, and again you are saying that hexa. How can you say it is 43 hexa? If it is hexa, how can you pronounce it as 43? It is wrong analysis or wrong perception or wrong way of pronunciation. What is it here? I can say it is 4,000. It is a 4,000 only in decimal when it is multiplied with the 10 power 3. Once again, please wait. Let me use annotation. Right. So here it is a 4,000. When 4 is multiplied with 1,000, then only it is 4,000. That for that you need to multiply with 10 powers. Then only it is 4,869. It is applicable only in decimal. If the same number is in other number systems, we cannot pronounce it as 4,869. What is this 10 is indicating? What is that? Base or radix. Base or radix. What is this here? 10 here is a base or radix of a number system. How do you define base or radix of a number system? What is the 10 is indicating of decimal number system? Yes, 10 is decimal number system, but what is the 10 is indicating? The symbols we are using 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 10 symbols. Coming to binary, what is the radix? 2. If it is radix 2, the symbols we are using, 2 symbols, 0 and 1. If it is octal, 0 to 7, 8 symbols. In hexadecimal, R equals to 16, 0 to 9, A to F. Then, how do you define base or radix of a number system? The number of different symbols used to represent a number in a number system is called base or radix of a number system. What is it here? The number of different symbols used to represent a number in a number system is called base or radix of a number system. Durga Prasad. What is the problem? Right. How do you define base or radix of a number system? The number of different symbols used to represent a number in a number system. Is called base or radix of a number system. The number of different symbols used to represent a number in a number system is called base or radix of a number system. Decimal 10 symbols we are using. Binary 2 symbols we are using 0 and 1. Octal 8 0 to 7. Hexadecimal 16 0 to 9 A to F 10 symbols we are using to represent a number. So this is a base or radix of a number system. What is the base? Number of symbols we are using to represent a number. Moving to next slide. A number n in radix R is like this. A number is represented like this. Capital N is a number in radix R, in which if you are observing, here we have two parts, 1 and 2. What is the first part? Integer part. The other part is fraction part. These two are separated by radix pointer. Remember this one. Don't say it is decimal point. In decimal number system, it is decimal point. But in other number systems, you cannot say that decimal point. If it is binary number system, binary point. So in general, we say it is a radix point. It is radix point. What is here? A number is consisting of two parts. One is integer part, other one is fraction part. Fraction part. Now, if R is the radix, then R power 0, R power 1, R power n minus 2, R power n minus 1, R power n. What about this? R power minus 1, R power minus 2, R power minus m. R power minus m. Just a minute. Right? Remember these words for online classes. You might be having some disturbances that may be bandwidth issues. That is our local issues. Right? So if everyone is not getting voice, then there is a problem with me. But only one or two have been facing some problems means that may be bandwidth issues locally. Check your speed, right? Very few have been mentioning about voice and all. So for them, I'm requesting, check your bandwidth, check your speed, internet speed. There might be an issue with your internet. Some people might be using mobile data. For them, please check your internet. That might be issue with your device, right? Manasa, Manasa. Chakravarti, Debojit Chakravarti. Wait. Manasa. Still are you facing problem? Is it audible now? Can you please respond, others? Is it audible? Yes. For everyone, it is clear. Right, right. Okay, okay. Thank you, thank you. Few sufficient, right? Many have responded. Thank you. It's very clear, right? My side, everything is clear. Yes, thank you. Right. When radix is r, we are writing here r power 0, r power 1, r power 2, and so r power n. Coming to fraction part, r power minus 1, r power minus 2, so r power minus m, r power minus m. The first thing about a number is consisting of two parts. One is integer, other one is fraction. These two are separated by a point. We name it as a radix point. In decimal, decimal point. In binary, binary point. In general, radix point. If r is the radix, we are writing here values for the position r power 0, r power 1, so r power n in integer part. What about fraction part? R power minus 1, r power minus 2, r power minus m. This r power n's are called, to understand this, what we say here, coming to decimal number, here ones, tens, hundreds, thousands. That is a value for the position. So here ones, tens, hundreds, thousands. So r power n's are giving value for the position or weight for the position or positional weight. In short, we name it as a weight of the position. It is weight of a position. What is it here? R power n's are called weight of the positions. Right? Ones, tens, hundreds. Similarly, r power 0, r power 1, r power n's in integer part, r power minus 1, r power minus 2, so r power minus m in fraction part. These are called weights of the positions. Weights of the positions. Now, in the previous slide itself, value for this position is what? 1000. Value of 4 is 4000. How do you get that 4000? 4 is multiplied with 1000. 4 is multiplied with 1000. That is 4000. Understand correctly? 1000 is the value for the position. Value of digit 4 is 4000. Then what we can say? Digit is multiplied with weight. Then we are getting value of digit because of its position. Because of its position. Once again, what is it here? Value for the position is weight. Value of a digit because of its position. Because of its position is nothing but a digit into weight is nothing but weighted value. What is it here? Weighted value. R power n's are called weights. D and R power n's are called weighted values. Weighted values. Once again, terminology of a number. What is it here? Integer part, fraction part, radix point. Then R power n's are called weights. Dn R power n. What is it here? Digit into weight is giving weighted value of a digit in that position. Digit is 4 only. Because of its position, we are getting 4,000. So digit is different, weight is different. When you are multiplying digit with weight, then we are getting weighted value. Weighted value of a digit because of its position. So once again, let me revise this once again. Right. First thing we need to understand is base or radix of a number system. What is it? The number of symbols we are using to represent a number in a number system is called base or radix. Decimal 10, binary 2, octal 8. That number is indicating how many different symbols we are using to represent a number. Next, in this, what we have understood, a number is consisting of two parts. One is integer part, second one is fraction part, separated by radix point. And for each and every position, we are giving a value that is R power values, depending on position. Depending on position, we are giving a value which are nothing but R powers, which are named as weights of the positions. And value of a digit because of its position is what? Digit into weight is giving weighted value. Is giving weighted value. Try to understand points correctly. Weight and weighted value. R powers are called weights. Digit into R power n's are called weighted values. Moving to next slide. Right. Most commonly used number systems in our digital circuits is first one, decimal R equals to 10. The symbols we are using 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Similarly, binary R is equals to 2. The symbols we are using 0 and 1. Right? Octal number system R is equals to 8. The symbols we are using 0, 1, 2, 3, 4, 5, 6, and 7. Similarly, hexadecimal number system. R is equals to 16. The symbols we are using 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A, B, C, D, E, and F. These are symbols we are using in hexadecimal. 0 to 9, A to F. Decimal equivalents of symbols A to F. 10, 11, 12, 13, 14, and 15. These are decimal equivalents of symbols A to F. Most commonly used number systems in our digital circuit design. Right? Binary, octal, hexadecimal. Now, in decimal, R equals to 10. In decimal, R equals to 10. Decimal equivalents of symbols 0 to 9. In binary, R equals to 2, 0 to 1. In octal, R equals to 8, 0 to 7. In hexadecimal, R equals to 16. Decimal equivalents starting from 0 to 15. So, in a number system with radix R, decimal equivalents of symbols ranging from 0 to R minus 1. Am I right? In a number system with radix R, decimal equivalents of symbols is ranging from 0 to R minus 1. Decimal 0 to 9, R equals to 10. Binary R equals to 2, 0 to 1. Octal R equals to 8, 0 to 7. hexadecimal r equals to 16, 0 to 15. If radix is r, 0 to r minus 1. Decimal equivalence of symbols is ranging from 0 to r minus 1. Right? Next, in decimal r equals to 10. In decimal r equals to 10. How do you write 10 in decimal? 1 0. Follow my words correctly. Right? In decimal r equals to 10. Radix is 10. The 10 we are writing in decimal is what? 1 0. In binary r equals to 2. How the 2 is represented in binary? In binary, 2 is 1 0. After 0 1, next number in decimal is 2. But in binary, we write it is 1 0. Similarly, octal r equals to 8. 8 is not a symbol in octal. 8 is represented with 1 0 again. After 7 in octal, next number is not 8. 8 is not a symbol in octal. 8 is represented with 1 0. Similarly, hexadecimal 0 to F. Next number is what? 16. 16 in hexadecimal is not having one symbol. Should be written with 1 0. Decimal r equals to 10, 1 0. Binary r equals to 2, 2 is represented with 1 0. Octal r equals to 8, 8 in octal, 1 0. Hexadecimal r equals to 16, 16 in hexadecimal is 1 0. That means r in radix r is 1 0 base r. Conclusion is what? In any number system with radix r, radix value r is represented with 1 0. In any number system with radix r, radix value r is represented with 1 0. Decimal r equals to 10, 10 is represented with 1 0. Binary r equals to 2, 2 is represented with 1 0. Octal r equals to 8, 8 is represented with 1 0. Hexadecimal r equals to 16, 16 is represented with 1 0. These are basic things we need to understand. Let me repeat two statements about these two observations. First one is, in any number system with radix r, decimal equivalence of symbols ranging from 0 to r minus 1. In any number system with radix r, decimal equivalence of symbols is ranging from 0 to r minus 1. Second statement, in any number system with radix r, radix value r is represented with 1 0. Whatever we are writing, that subscript is indicating base of the number system. 1 0 subscript r, 1 0 base r, 1 0 base r. Try to understand correct. What is it here? 1 0 base r. In any number system, the radix value r is represented with 1 0 base r, 1 0 base r. Right. I hope it is clear till now. Moving to next slide. Right. Now, after understanding basics of number systems, what we have understood till now, what is base or radix, what are the symbols possible in each and every number system, and what is the decimal equivalence possible in each and every number system, then how we represent a radix value in a number system. How we represent a radix value in a number system. Right. Now, let us see. Next thing is a base or radix conversion. Everyone knows, let me do a quick revision on this. Base conversions or radix conversions. Base or radix conversions. What do you mean by this? A given number is in one number system, we want to get equivalent in other number system. A given number is in one number system, we want to get a equivalent in other number system. That's what we want to do. In that first one, let me consider decimal to Veerababu. Decimal to any other base. First conversion, let us see decimal to any other base. What do you mean by this? Given number is in decimal, we want to get equivalent in other number system. We want to get equivalent in other number system. What is it here? A number is in decimal. We want to get equivalent in other number system. Then, how to convert the decimal to the required base? Immediately people say that divisions. Divisions we are doing. Then we need to consider reminders in reverse order. Is it completing? No, 50% only. That is only for integer part. That is only for integer part. Let me say once again. Divisions. In each division, it is producing reminder. These reminders must be considered in reverse order. That is for integer part. What about fraction part? Multiplications. Decimal fraction part is multiplied with required base, and every multiplication is producing integer part. These integers must be considered in original order. Let me repeat once again 2 steps. While converting decimal to any other required base, while converting from decimal to any other required base, what can we do here? Let us see. The first step is integer part. To get integer part in required base, what do we do? Taking successive divisions of decimal integer part with required base. In this, accumulating reminders in reverse order. Second one is getting fraction part. To get fraction part in required base, taking successive multiplications of decimal fraction part with required base and accumulating integers produced in original order. Original order. Once again, I am repeating for you. Right? To get integer part in required base, taking successive divisions of decimal integer part with required base, accumulating reminders in reverse order. To get fraction part, take successive multiplications of decimal fraction part with required base, again accumulating integers in original order. Original order. Let me take example is 319.6875 decimal. Convert to binary, octal, hexadecimal and base 4. Once again, the decimal number given is 319.6875. I can say 319. The reason is it is in decimal. There it is, hundreds, thousands is applicable. 319.6875 is decimal number. Find binary, octal, hexadecimal and base 4 equivalent. What is it here? Binary, octal, hexadecimal and also base 4 equivalent. This is what we want to calculate. Decimal to binary, octal, hexadecimal and base 4 equivalent. Let us see first binary equivalent. What is the number given? This is a number given. To get binary, what should I do? Divisions of integer part with base 2, multiplications of fraction part with base 2. So 319 divisions with 2. 2 ones are 5s are 9s are. Remainder is what? 1. And again 2 7s are 9s are. Remainder is 1. 2 3s are 9s are. Remainder is 1. 2 1s are 9s are. Remainder is 1. 2 9s are. Remainder is 1. 2 4s are. Remainder is 1. 2 2s are. Remainder is 0. 2 1s are. Remainder is 0. These reminders must be considered in reverse order. Then what is that here? 1 0 0 1 1 1 1 1 1 is a integer part. Is integer part. Then we want to get a fraction part. How to get fraction part? 0.6875 is multiplied with 2 is equals to 1.375. What is integer part in this? 1. And remaining fraction part is a 0.375 into 2 is equals to 0.75. What is integer part? 0. Remaining fraction part 0.75 into 2 is equals to 1.5. Here integer is 1. Then again 0.5 into 2 is equals to 1.0. What is it here? 1. As fraction part is becoming 0, we can leave a multiplication there itself. Sometimes fraction part may not be becoming 0. Then continuously you are getting non-zero fraction part. Then I should observe, is there any repetition or not? If there is any repetition, then we can put a bar on digits which are getting repeated. Continuously we are getting non-zero fraction part. Then there will be some digits which are getting repeated. We can put a bar, then that is the equivalent. Then in this fraction part is becoming 0, there we can wind up. Then what is the fraction part here? 1 0 1 1. This is a binary equivalent. That is a binary equivalent. For the given decimal number, the binary equivalent is a 100111111.1011 is a binary equivalent. Is binary equivalent. Similarly, complete that octal, hexadecimal, and base 4 of same number. Octal, hexadecimal, and base 4 equivalent of same number. Give me a minute. Yes. If I do octal equivalent, decimal number given is a 319.6875. Now to get octal equivalent, 319 divisions with 8. 8 threes are 24, right? Remainder is 7, 79. 8 9 is 72. Remainder is 7. Then again, 8 4s are 32. Remainder is 7. What is it here? 477 is integer part. Whatever fraction part, 0.6875 is multiplied with 8. Can you help me? What is it? 5.5. What is integer part in this? 5. 0.5 into 8 is equals to 4.0. What is integer part? 4. Then what is that integer part? Sorry, fraction part 5 4. Then what is that base 8 equivalent of given decimal number is 477.4.54 is a octal equivalent. Is a octal equivalent. Coming to hexadecimal, 319 divisions with 16. 16 1 is 16, remainder is 15. 159, 16 9 is 144, remainder is 15. Then again 16 1 is 16, remainder is 3. So what is it 15 here in hexadecimal? It is F. Then 13F is a integer part. Whatever fraction part, 0.6875 is multiplied with 16, which is 11.0. 11 is integer part, symbol is B. So 13F point B is a hexadecimal equivalent. 13F point B is hexadecimal equivalent of given binary number. Similarly, if you would like to get a base 4 equivalent, you can try. 319 divisions with 4. 4 sevens are 28, 39. 4 9 are 36. Remainder is 3. 4 1 are 4, 39. 4 9 are 36. Remainder is 3. 4 4s are 16. Remainder is 3. 4 1s are 4. Remainder is 0. Then 1 0 3 3 3 is integer part. Whatever fraction part, 0.6875 multiplied with 4 is a 2 point. How much is that? 2.75. Right. Then in this integer part is what? 2. 0.75 is multiplied with 4 is equals to what here? 3.0. Now 3. Then 1 0 3 3 3, right? 0.23 is a base 4 equivalent of given number. Is base 4 equivalent of given number. Right? That's the way we convert from decimal to any other required base. Decimal to any other required base. Now, next is any base 2 decimal. Any base 2 decimal. What is this any base 2 decimal? We want to calculate a decimal equivalent of a number which is in other than decimal number system. Point should be understood correctly. We want to calculate a decimal equivalent of a number which is in other than decimal number system. How to calculate? Simple thing. What is it here? Multiply, add, multiply, add. What is it exactly we are observing? When you are multiplying, what is happening? Digit is multiplied with weights. R powers we are multiplying. So digit into R powers which are weights, digit into weights are called weighted values. Then what we are doing? Adding all these weighted values. Is nothing but taking summation of weighted values of all digits. To get decimal equivalent of a number, what we are doing? Taking summation of weighted values of all digits. Simple way. Simple statement which is giving clarity. What is it here? Instead of saying that multiply, add and so, what we can say? Take summation of weighted values of all digits. To get decimal equivalent of a number, take summation of weighted values of all digits. Let us see some examples to get more clarity. So just a quick revision. What I'm doing here is a quick revision which we know already. Right? Some of you may be new to this concepts. For few people who have been expecting these basics also, for them I'm covering. Already we know this, but the terminology we may not be knowing. With terminology, let us get concepts clear. So we know these conversions, a quick revision with the terminology. So instead of just multiply, add, what we can say? Simple way, take summation of weighted values of all digits. Example, if I say 100,111.011 binary number, find decimal equivalent. Find decimal equivalent. Similarly, octal number, find decimal equivalent. Hexadecimal number, find decimal equivalent. One by one, let us calculate. We need to find decimal equivalents of these numbers. For binary, what we need to write? 2 power 0, 2 power 1, sorry. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. And similarly here, 2 power minus 1, 2 power minus 2, 2 power minus 3. What we have written first? Weights. Then what should I do? Weighted values. 1 into 2 power 5, 32. Plus 0 into 2 power 4, 0. 0 into 2 power 3, 0. 1 into 2 power 2, 4. 1 into 2 power 1, 2. 1 into 2 power 0 is 1. 0 into 2 power minus 1, 0. 1 into 2 power minus 2, 1 by 4. 1 into 2 power minus 3, 1 by 8. Then getting decimal equivalent, 32 plus 4 plus 2 plus 1 plus 1 by 4 is 0.25, 1 by 8 is 0.125. Then 32 plus 4 plus 2 plus 1 is 39.375 is a decimal equivalent. Is decimal equivalent. For given binary number, decimal equivalent is 39.375. Similarly, octal number. For this, first we need to write weights. 8 power 0, 8 power 1, 8 power 2. Next, 8 power minus 1, 8 power minus 2. Then finding decimal equivalent. What is it here? 2 into 8 square is 64. Plus 3 into 8 power 1 is 8. Plus 7 into 8 power 0 is 1. 2 into 8 power minus 1, 1 by 8. 4 into 8 power minus 2, 1 by 8 square, 1 by 64. Then 128 plus 24 plus 7. 2 1 ja 2 4 ja 1 by 4 is 0.25 plus 4 1 ja 4 16 ja 1 by 16 is 0.0625. Then 128, 152, 159.3125 is a decimal equivalent of given octal number. Decimal equivalent of given octal number. What we are doing? First writing weights, then taking weighted values, then summation of weighted values. Similarly, for hexadecimal number, 16 power 0, 16 power 1, 16 power 2, 16 power minus 1. Let us calculate decimal equivalent. What is A? 10, 16 square, 256, plus 3 into 16 power 1 is 16. F is 15, 16 power 0 is 1. What is C? 12 into 16 power minus 1 is 1 by 16. Then 10 into 256 is 2560 plus 16 3s are 48, 15 1s are 15, then 4 3s are 4 4s are 3 by 4 is 0.75. Then 2560 plus 48, 2608 plus 15, 2623.75 is a decimal equivalent of given hexadecimal. Decimal equivalent of given hexadecimal. A simple thing is taking summation of weighted values of all digits. Taking summation of weighted values of all digits is giving decimal equivalent of a number. Decimal equivalent of a number. What we have done here? Decimal to any base. Now, second one is what? Any base to decimal. Next. Balakrishnan. Wait. Is in base 9. Find base 3 equivalent. Question is a number is given in base 9. Find base 3 equivalent. Find base 3 equivalent. A number is given in base 9. We need to find base 3 equivalent. Then what we can do? Converting to decimal, then decimal to base 3. Converting to decimal, decimal to base 3. It is a very lengthy process. It is very lengthy process. Then what we can do? Let us do some observations. What is it? Let us see. What is the conversion? Base 9 to base 3. Base 9 to base 3. Are you observing any relation between these two? Yes. 3 square base to 3 base. Or example, b power n base to b base. When this is satisfying, I don't need to convert entire number into required base. When b power n to b is satisfying, when b power n to b is satisfying, I don't need to convert entire number into required base. Digit by digit, individually, independently can be converted to required base. It is not a new method we are learning. Already we know this. What is it? Octal to binary. Octal to binary. What we are doing? Digit by digit is replaced with the 3-bit equivalent. Hexadecimal to binary. Each symbol is represented with the 4-bit equivalent. Why? Octal to binary. 2 power 3 base to 2 base. N value is 3. Hexadecimal to binary. 2 power 4 base to 2 base. That means n value is 4. Each symbol is represented using 4 bits from hexadecimal to binary. It is not only for octal to binary, hexadecimal to binary. It is for every b power n base to b base. Whenever conversion is from b power n base to b base, I don't need to convert entire number into required base. Digit by digit independently, we can replace with n digit equivalent. Compulsory, I need to use n digits. Point should be understood correctly. Whenever it is conversion from b power n base to b base, each symbol in b power n base should be represented using n digits in base b. To get equivalent in base b, replacing each and every digit in base b power n with base b equivalent using n digits. Here n equals to 2. Each and every symbol in base 9 should be replaced with the 2-digit equivalent. Whether it is required or not required, you must use n digits. Here 2 digits. Once again, while converting from base 9 to base 3, each symbol in base 9 should be represented using 2 digits. Using 2 digits. Let us see how is it. So 6 in base 3. What is it here? 6 in base 3. 3 2s are remainder is 0. Then what is it here? 2 0. What about 0? 0 in base 3 is what? 0 only. But I need to use 2 digits. Then 0 0. Point should be understood correctly. Compulsory, I need to use n digits. Here 2. So 2 digits. So each symbol should be represented using 2 digits. 6 is represented with 2 0. 0 is represented with 0 0. What about 5? 3 1s are remainder is 2. What is it here? 1 2. What about 7? 3 2s are remainder is 1 2 1. Point. What about 8? 3 2s are remainder is 2. Then what is it here? 2 2. What about 2? 2 is 2 only, but I need to use 2 digits. Then 0 2. That is base 3 equivalent. Not more than 30 seconds. Once you are understanding the method we are using, b power n base to b base. Whenever it is converted from b power n base to b base, digit by digit can be replaced with n digit equivalent. Here 3 square base to 3 base. That means each and every symbol in base 9 should be represented using 2 digits. Should be represented using 2 digits. So n value is 2. Base 9 symbol is replaced with 2-digit equivalent in base 3. Base 9 to base 3. 3 square base to 3 base. So simply replacing digit by digit or symbol by symbol with equivalent using 2 digits. Using 2 digits. Dinesh. Sorry. Pratik, Pramod, Naveen Kumar. I'll discuss. In the next, I'm going to give you full clarity about this method itself. Yes, Shane Bhagavalli. Wait, yes, right? You will understand this entire thing with next some more examples. Until that, hold on. So what is that here? Simple thing is whenever it is b power n base to b base, each symbol in b power n should be replaced with n digit equivalent. Must use n digits. Digit by digit, symbol by symbol should be replaced. Symbol by symbol should be replaced with base b equivalent. Must use n digits. Here n equals to 2. Each symbol is replaced with 2 digits equivalent in base 3. In base 3. Let us take a small break for 15 minutes from now. We'll resume in 15 minutes and we continue. Let us take 15 minutes break from now. We'll resume in 15 minutes. We'll continue. Fine. Right. Welcome back. Right. Shivalila, wait. Joseph, thank you. I'll consider your request. Yeah, Srinath, I'll let you know about that material, sir. Yeah, Ravi Teja. Yeah, Sahil Singh. I'll update with that information. Okay. Okay. As I'm not able to see your faces, whether you are understanding or not. Yes, it happens, sir. Okay. I consider your request, sir. Sure. Any other issues, sir? Some people are requesting to slow down when theory part is going on. They're requesting to slow down. Okay, I do that. Sandeep, you should say, what is that? Yeah, Abhijit, wait. Yeah, Pratik, Pramod, Pratyush Kumar, because you need to consider everyone. The coaching is for all, it is not only for few, right? Pratyush Kumar, you have to accept when people are slow in accepting. Yeah, Pratik Pramod, what type of notes you are expecting? Yeah, Sahil Singh, day by day you are getting that updated PDF. You'll be getting. Ashutosh Kedari. Yeah, Sai, Banawat Sai. Yes, sir. You'll get that. With the limited access, limited number of access, there will be availability of watching this video again. Madhusudan, I can complete in 2 days. Do you need completion or coverage? Yeah, Yugasri, I'll talk about that. Wait. Yeah, Gopalakrishna Reddy. That will let you know all this information. I'll talk to our managers. I'll let you know about this, whether you will be able to collect the material physically or not. I will let you know. Yugasri, wait, I'll discuss about that number of zeros and number of digits. Yeah, Vamshi Krishna, Karanam, I'll mention that. Okay, if I keep on reading your messages, I'll be here only. Okay, I consider your request about slow down while discussing theory part. I do that. I agree, because as it is not physical classes or offline classes, we cannot see what is happening in the class, right? Okay, stop messaging, please. Right now, here some people were asking about what is this exactly. Let me repeat once again. Not only for 9 to 3, any number or any base to another base which is satisfying b power n base to b base. B power n base to b base. Not only octal to binary, not only hexadecimal to binary, not only 9 to 3, whichever the base which is satisfying from b power n to b is the conversion. Then each and every symbol or digit in base b power n can be replaced with n digit equivalent of base b. Point should be understood correctly. N digit equivalent of base b. N digit compulsory. You need to replace each and every digit with n digits only. To make it equal, to get equivalent, you must use n digit for representing each and every symbol in base p power n. That is the reason 0 is also replaced with 2 zeros. 0 in base 3 is 0 only. But I must use n digits. As n is 2, 0 is replaced with 2 zeros. Right? 2 in base 3 is 2 only. Understand point correctly. Right? I thought of discussing all these after the break only. People have been thinking correctly. Right? Raised very good doubts. Follow correctly. Each and every digit should be replaced with n digits compulsory. Then 2 is replaced with 0, 2. 2 in base 3 is 2 only. Why? In base 3, the possible symbols are 0, 1, 2. But in base 9, 2 means in base 3 also 2 only. But I must use 2 digits. That is the reason appending 0, we are writing it as a 0, 2. So, each and every symbol in base b power n should be replaced with n digit equivalent in base b. Karthikeyan, Tasni. Wait, I'll give a chance to, right? Doubts at the end. Wait. Right? Let me repeat once again. Whenever it is satisfying b power n base to b base, in all these cases, you can replace digit by digit with equivalent in base b by using n digits. By using n digits. Once again, each and every digit in base b power n should be replaced with n digit equivalent in base b. Must use n digits. That is the reason in this also 0 is replaced with 2 zeros because n equals to 2. So 2 symbols or 2 digits must be used in base 3 to represent a 0. That means 0 is replaced with 0, 0. 2 is 2 only in base 3 also. But I must use 2 digits. That is the reason I'm writing it as 0, 2. If it is 1 in base 9, for example, let me say that 301.27 is in base 9. If I would like to write a base 3 equivalent of this base 9 number, 3 is what? 1, 0. 3 in base 3 is 1, 0. R in base R is 1, 0. 3 in base 3 is 1, 0. What about 0? 0, 0. What about 1? 0, 1. I hope you are following. 1 is there in base 9. What is the base 3 equivalent? 1 only. But I need to use 2 digits. That is the reason it is 0, 1. Point 2 is 2 only. But I need to use 2 digits. 0, 2. 7 in base 3. What is it? 3, 2 the remainder is 1. What is that here? 2, 1. That is a base 3 equivalent. If anyone is having any doubts in this, let me know now. Let me clear those doubts and proceeding with next. What happened, Karthikeyan? Karthikeyan? Why are you raising your hand? Karthikeyan. Please check. Unknowingly, you might be pressing that raise hand. Please. Shubha Sinha, Sudha Sinha. Naveen. What happened? I told you already at the end, I'll give you a chance to talk. Why are you raising your hands? Check it. Deboji Chakrabarti. Chakrabarti. Right. I told you already, please don't interrupt me. Don't interrupt the class. 200 plus people have been waiting. I will address your doubts, individual doubts. I'll give you my number also. Right? I'll be there to help you. Right? Right. Any doubts now in this? How we got 0221? First rising and first interaction. Okay. Yeah. Srinivasa Manikanta Surya Namburi. Right. Yes. Annapurni, please wait. See. 3 in base 3 because the number is in base 9. So in base 9 symbol is 3. In base 3 what is equivalent to 1 0. 0 is what? 0 only, but I need to use 2 digits. So 0 0 1 means what? 1 only in base 3, but I need to use 2 digits because of that 0 1. Now 2 in 2 in base 3 is 2 only, but I need to use 2 digits. That is the reason 2 is becoming 0, 2. Right. Next, 7 in base 3. 7 in base 3. 3 2s are, remainder is 1. What is this? 2 1. 7 is replaced with 2 1. 2 is 2 only, but I need to use 2 digits. So 0 2. 1 is 1 only. 0 1. 0 is 0 only. 0 0. 3 is 1 0 in base 3. I hope no doubt in this. I'm moving to next slide. Moving to next slide. Please don't raise your hands, please. Otherwise, I won't look at queries as well as raising hands. Sometimes there may be problem, right? Right. Wait, Dinesh Sai. Wait. Everything will be cleared. Right? Now. So similarly, the possible base values, if we are observing, base 8 2, base 2. What is it here? 2 power 3 base 2, 2 base. In base 8, what is the possible symbols? 0, 1, 2, 3, 4, 5, 6, 7 are possible symbols. Now, how many bits I need to use in binary? 3 bits. Right? 0 is 0, 0, 0. 1 is what? 0, 0, 1. 2, 0, 1, 0. How am I getting this? Same procedure. 3 in base 2 is 0, 1, 1. 4, 1, 0, 0. 5, 1, 0, 1. 6, 1, 1, 0. 7, 1, 1, 1. The symbols are in base 8, that is 2 power 3 base. And equivalent in base 2 is nothing but replacing each and every symbol with 3-bit equivalent. Correct? With base 2 equivalent. How many bits I need to use? 3 bits. Why? N value is 3. Now, 16. 2, 2. That means 2 power 4 base 2, 2 base. So what we have in 16 base? 0, 1, 2, 3, 4, 5, 6, 7. Let me use another column. What is that here? 8, 9. Next, A, B, C, D, E, and F. So 0 in base 2. 0 is in hexadecimal. What is base 2 equivalent? 4 zeros. N zeros we are writing. 1 is 0, 0, 0, 1. 2, 0, 0, 1, 0. 3, 0, 0, 1, 1. 4, 0, 1, 0, 0. 5, 0, 1, 0, 1. 6, 0, 1, 1, 0. 7, 0, 1, 1, 1. What about 8? 1, 0, 0, 0. Next 9, 1, 0, 0, 1. 1, 0, 1, 0. D is what? 1, 0, 1, 1. Next, C is 1, 1, 0, 0. Next, 1, 1, 0, 1. 1, 1, 1, 0. 1, 1, 1, 1. 1, 1, 1. That is base 16 to base 4. If it is base 4 equivalent, if I would like to write, what is it here? 4 square base 2, 4 base. Then what should I do? Each and every hexadecimal symbol should be replaced with 2-digit equivalent in base 4. Base 16 to base 4. 4 square base to 4 base. I hope you are understanding. Now n value is how much? 2. That means each and every symbol in base 16 should be replaced with 2-digit equivalent in base 4. 0 is 0, 0, 1, 0, 1, 2, 0, 2, 3, 0, 3. Why? In base 4, possible symbols are 0, 1, 2, 3. 4 symbols possible. In base 4, the possible symbols are 0, 1, 2, 3. Now 4 in base 4. What is 4 in base 4? 1, 0. Next 1, 1, 1, 2, 1, 3. And here 2, 0, 2, 1, 2, 2, 2, 3. Next 3, 0, 3, 1, 3, 2, 3, 3. Base 16 to base 4. Check it. 15 in base 4. 4 3s are 12. Remainder is 3. 3, 3. So base 16 to base 4. That means 4 square base to 4 base. N value is 2. Each and every symbol in hexadecimal should be replaced with 2-digit equivalent in base 4. Now, similarly, base 9 to base 3. That is 3 square base to 3 base. Base 9, what we have? 0, 1, 2, 3, 4, 5, 6, 7, 8. Then each and every symbol in base 9 should be replaced with 2-digit equivalent in base 3. 0 is 0, 0, 1, 0, 1, 2, 0, 2, 3, 1, 0. Next 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. I hope everyone is understanding what I'm using logic in this. It is not only for octal to binary, hexadecimal to binary. It is from base b power n to base b, b power n base to b base, b power n base to b base. I hope it is clear now. Mirza Amir, can you please mention where you did not understand? Where you did not understand? Which one you did not understand? Yes, I'll try to help you. Please let me know where you were not able to follow. Mirza. Please type the message where you are lying. Right. Gopal Krishna Reddy. From the first minute onwards, you have been asking doubts other than subject. Right. Abhijit is asking about green column. Neja, I did not get any response from you. All clear now? Right. Okay. This green column, someone is asking. So base 16 to base 4. That means 4 square base to 4 base. That means each and every symbol can be replaced with a 2-digit equivalent in base 4. In base 4, the possible symbols are 0, 1, 2, 3. 0, 2, r minus 1. In base 4, what is the possible? 0, 1, 2, 3. That means here 4 square base to 4 base means n value is 2. Each and every symbol in base 16 should be replaced with a 2-digit equivalent. 0 in base 4 is 2 zeros. 1 in base 4 is 1 only, but I need to use 2 digits. That is the reason 0, 1. 2 in base 4 is also 2 only. That is 0, 2. 3 in base 4 is 3 only. That is 0, 3. Now 4 in base 4, no doubt it is 1, 0. 5, 1, 1. 6, 1, 2. 7, 1, 3. Next 8, 2, 0. 9, 2, 1. 2, 2, 2, 3. 3, 0, 3, 1. 3, 2, 3. And the base 9, that means 3 square base to 3 base means n value is 2. Once again, each and every symbol in base 9 should be replaced with the 2-digit equivalent. 2-digit equivalent. Right. Now, let me take some more examples to get more clarity. Find binary equivalent of base 8, binary equivalent of hexadecimal, binary equivalent of octal, binary equivalent of hexadecimal. While calculating binary equivalent of octal, what should I do? Replacing each and every symbol with 3-bit equivalent. 6 is what? Now I'm writing directly 1, 1, 0. 0 is what? 0, 0, 0. 1 is what? 0, 0, 1. 7 is what? 1, 1, 1. 3 is what? 0, 1, 1. That is a binary equivalent of octal number. Replacing symbol by symbol. I hope everyone is able to understand. 6 is 110. 0 is 000. 1 is 001. 7 is 111. 3 is 011. What about D? From hexadecimal to binary. 1101. 0 is what? 0000. 4 zeros. 9 is what? 1001. F is what? 1111. What about 3? 0011. This is a binary equivalent. Simply converting base b power n to base b, replacing symbol by symbol, digit by digit. Right. Now, we have seen b power n base to b base. Now it is b to b power n. If it is b to b power n, then what should I do? B to b power n. What we have done till now? B power n, higher base to lower base, which is satisfying b power n to b. Now b to b power n, lower base to higher base. For example, binary to octal, binary to hexadecimal, base 3 to base 9, base 4 to base 16. In such cases, what can we do? Well, converting from lower base to higher base, which is satisfying b to b power n, which is satisfying b to b power n. Then already we know grouping n digits. In base b, we are finding sets of n digits. Then finding decimal equivalent of each set individually and using respective symbol for decimal equivalent. Follow my words correctly. Again, I'm repeating. While converting from b to b power n, lower base to higher base, which is satisfying b to b power n. In such cases, what can we do? The first step is finding sets of n digits. In the given number, finding sets of n digits. Then second step is finding decimal equivalent of each set individually. Third step is using symbol for decimal equivalent. That's it. In base b power n, what is the symbol for the decimal equivalent? That must be used. Once again, I'm repeating. Some people are slow. For them, I'm repeating. So focus on this, right? While converting from base b to base b power n, the first step is finding sets of n digits. Second step is finding decimal equivalent of each set. Third step is using using symbol for the decimal equivalent. I keep on repeating again and again. Will be same if you're not focusing on my words. Let me take example to give you clarity. For example, find octal and hexadecimal equivalents of a binary. Find octal and hexadecimal equivalent of this given binary. To find octal equivalent, what is the first step? Grouping 3 bits. To find octal equivalent, the first step is grouping 3 bits. In the given number, it is binary. Right? It is binary. We want to find octal equivalent. To find octal equivalent, the first step is finding 3 bits. Sets of 3 bits. Then 3, 3. Number of bits is not sufficient. Then appending zeros. Assuming we are in unsigned numbers. Clear? Get clarity about my words. What is that here? Assuming we are in unsigned numbers, we can append zeros. It is not applicable always. It may be required to append with ones also sometimes. That we understand after getting into signed numbers. Until that, hold on. So at this moment, I'm explaining once again. So we are finding sets of 3 bits. So if you start grouping from least significant digit in integer part, so grouping 3 bits, 3 bits. Now number of bits, 1 is remaining. We need to group 3 bits. So appending 2 zeros. Appending zeros is applicable in unsigned numbers. Assuming we are in unsigned numbers, we are appending zeros. It is not correct in signed numbers. Signed numbers extension is different that we discuss later. Until that, hold on. So next, in fraction part again, 3 bits as number of bits is not sufficient, appending it. Then what happens here? This 0, 0, 1 is representing 1. 0, 1, 1 is representing 3. 1, 1, 1 is representing 7. 1, 0, 1 is representing 5. 1, 1, 0 is representing 6. This is the octal equivalent of given binary. Simple thing. 0, 0, 1 decimal equivalent is 1. Symbol is 1. 1, 0, 0, 1, 1 decimal equivalent is what? 3. The symbol is 3. 1, 1, 1 decimal equivalent is 7. Symbol is 7. 1, 0, 1 decimal equivalent is 5. Symbol is 5. 1, 1, 0 decimal equivalent is 6. Symbol is 6. For the same number, let us find the hexadecimal equivalent. 1, 0, 1, 1, 1, 1, 1. Point 1, 0, 1, 1, 1. Right. We want to find a hexadecimal equivalent of a same binary. For that, what should I do? Grouping 4 bits. 4. Number of bits is not sufficient, appending a 0. Again, 4. Number of bits is not sufficient, appending 3 zeros. One by one, let us convert. 0, 1, 0, 1. What is that here? 5. 1, 1, 1, 1. 15. I'm not writing 15. That's what I've been saying. What is that here? Use symbol for the decimal equivalent. Decimal equivalent is 15. Symbol is F. Point 1011. Decimal equivalent, if you are calculating using 2 power 0, 2 power 1, 2 power 2, 2 power 3, it is 11. 11 symbol is what? B. And 1000, it is 8. So decimal equivalent is 8. Symbol is also 8. Right? Any questions? Some people were asking how to convert b to b power n. Let me give you one more example also. Is in base 3. What is base 9 equivalent? It is in base 3. What is base 9 equivalent? What should I do now? First thing is grouping 2 digits. 2 digits. 2 digits. Appending a 0. 2 digits. 2 digits. Appending a 0. Then 0, 1. How to write? 0, 1. 3 power 0. 3 power 1. What we get here? 0 plus 1, it is 1. Again 0, 1, it is 1. 2, 2. What should I do? 3 power 0, 3 power 1. 3 2 is 6 plus 2 into 3 power 0 is 3 power 0 is 1. So 6 plus 2 it is 8. See, 2 1. So 3 power 0, 3 power 1. Decimal equivalent. 3 2 is 6 plus 1 it is 7.10 is what? 3. 3. Sorry, I made a mistake. It is 2. Let me take it as 2. Sorry, it is not 3. It is 2. Then 2 2. What we get 2 2? Again 8. 2 0. 2 0 means what? 3 power 0, 3 power 1. 3 to the 6 plus 1 it is, sorry, 3 to the 6 plus 0 it is 6. That is a base 9 equivalent. Let me know if I do any mistake. 0 1 is 1, 0 1 is 1, 2 2 is 8, 2 1 is 7, 1 0 is 3, 2 2 is 2 2 is 8. Right. So that is the base 9 equivalent. Whatever it is that, if it is b to b power n, lower base to higher base, which is satisfying b to b power n, the first step is grouping n digits. Second step is finding decimal equivalent of each set, then using respective symbol for decimal equivalent. That's what b to b power n. B power n to b, that's what we have discussed earlier. We started here with example. So base 9 to base 3 we have converted. Then we understood what is the process with examples. Then we have seen b to b power n. Sorry, these again examples on b power n to b. Then we are seeing that b to b power n, b to b power n. right? What is the conversion so far we have discussed? Decimal to any base to decimal, then b power n to b to b power n. If not these, for example, a number is like this. Is in base 4. What is the base 7 equivalent? I cannot use any of the methods so far we have discussed. Then what should I do? No alternative. Converting to decimal to required base. Converting to decimal to required base. No alternative. Some people are asking, if not, what should we do? Yes, no alternative. Right, calculating decimal equivalent again from decimal to required base. So in this, what should I do? Converting decimal to required base. No alternative for that. Right. Those are conversions which we must know, which we must understand. Right now, second possible way, frequently we have been getting questions is by giving an equation, they have been asking what is the possible base values which can satisfy given equation. Once again, by giving an equation, they are asking what is the possible base values which can satisfy given equation, right? Let me take one example, then you may get clarity. For example, 2, 3 plus 2, 2 is equals to 1, 0, 0. What is the base value which can satisfy this equation? Please don't say that it is wrong. It is wrong with respect to our comfortable number system, which is decimal. Because 23 plus 22 is 45, that we know. But 2, 3 plus 2, 2 is equals to 1, 0, 0 is given in unknown number system. Then what can be the base for this equation? What is the base value which can satisfy this equation? What is the base value which can satisfy this equation? Right. In such cases, how to proceed to calculate base values? Then how to proceed is unknown is base. Let me say that unknown is x. Let me say this equation is valid in base x. X is unknown. Then let us calculate x values. As we are comfortable in decimal, what should I do? Convert each number into decimal. Understand correctly? So this equation is valid in x base. Assuming x is the base, we need to calculate x values. Let us see what is the decimal equivalent of each number, assuming base is x. Then x power 0, x power 1, x power 0, x power 1, x power 0, x power 1, x power 2. Right? So here, assumed base is x, then we are proceeding. What is decimal equivalent of 2, 3? 2x plus 3 plus what is decimal equivalent of 2, 2? 2x plus 2 is equals to what is decimal equivalent of 1, 0, 0? X square plus 0 plus 0. I hope everyone is able to write decimal equivalents. Then what can be the equation? X square minus 4x minus 5 is equals to 0. Are you able to get this one? 2x plus 2x is 4x, taking other side, minus 4x. 2 plus 3 is 5, minus 5. X square minus 4x minus 5 equals to 0. Now, solve this. X square minus 5x plus x minus 5 is equals to 0. I'm using decimal manipulation because numbers are converted decimal. Now, equation is in decimal. I can use decimal manipulations. Be clear about this. Each number is converted to decimal. Now we are getting an equation in decimal. Now I can use decimal manipulations to solve. If I take x common, x minus 5. If I take 1 common, x minus 5 is equals to 0. Then x plus 1 into x minus 5 is equals to 0. Then x equals to minus 1 or 5. Now we need to validate. We are getting x values. We cannot accept all these as base values because whatever the x we are getting are base values. How can I accept minus 1 as a base? I cannot have minus 1 base. Why? How can I use minus 1 number of symbols? What is base? Number of symbols we are using to represent a number. How can I represent a number using minus 1 number of symbols? Is it possible? Impossible, right? What do you mean by minus 1 symbols? Don't use give it back. Is it realistic? Can it be realizable? No. Minus 1 can't be the base. Negatives can't be the base. How can I use negative number of symbols to represent a number? To convey a quantity, I'm using symbols. So while using symbols, it can be a positive number. It cannot be a negative number. Minus 1 can't be the base. 5 may be the base. 5 may be the base. Let us validate that also. How can I validate? 2, 3 plus 2, 2. I'm adding these two numbers in base 5. Base 5. Now, see, equation we are validating whether it is correct or not in base 5. So minus 1 can't be the base. 5 is valid or not, we are verifying. 2 plus 3. 5. But we are in base 5. 5 is not a symbol in base 5. 5 is 1, 0 in base 5. Is there any doubt? I'm adding this position. We have 2 plus 3. 2 plus 3 is 5 decimally. But in base 5, 5 is represented with 1, 0. 1 plus 2 plus 2. 1 plus 2 plus 2 again, 5. 5 in base 5 again, 1, 0. Yes, when we are adding this 2, 3 plus 2, 2 in base 5, the resultant is 1, 0, 0 in base 5. Then it is valid. No doubt in that, it is valid. It is valid. The other way we can do validation like this. What is that here? 2, 3 plus 2, 2. Equation is what? 1, 0, 0. Whether it is correct or not in base 5, let us verify. Assuming base is 5, let me do that. 5 power 0, 5 power 1. Decimal equivalent we are calculating. 5 power 0, 5 power 1. Let us calculate decimal equivalent. 5 power 0, 5 power 1, 5 power 2. Then decimal equivalent of 2, 3 is what? 2, 5 is 10 plus 3 into 5 power 0 is 3. So 10 plus 3 is 13. Again 2, 5 is 10 plus 2 into 5 power 0 is 2. So 10 plus 2 is 12. What about RHS? 1 into 5 square 25 plus 0 plus yes. LHS decimal equivalent to 25. RHS also 25. Another way we can validate. One thing is if you are comfortable adding in other number system, we can go with that. Otherwise, we can go with the LHS decimal equivalent, RHS decimal equivalent. Try to focus on this. When equation is given, they are asking what is the possible base values which can satisfy that equation. We need to calculate base values which can satisfy that equation. Then, first step is assuming a variable for base. Calculating decimal equivalent of each number, assuming variable. Then getting an equation in decimal, solving for unknown variable using decimal manipulations. Then validate. Then validate. Let me repeat once again. Assuming a variable for base. Second step is finding decimal equivalent of each number. Then getting an equation in decimal, solving for unknown variable using decimal manipulation. After getting this, then we are validating. Here itself, we are confirming that -1 can't be the base. 5, we have tried to verify. Yes, it is valid. Yes, it is valid. Now, try everyone. Find base values which can satisfy this equation. Kashyap, that might be issue with your internet speed. Please check. Yes. If I assume base is x, then what we can write? 4 1 is equals to 5 square. Then 4 1 is equals to 25. As base is x, what we get here? 4x plus 1 is equals to 2x plus 5. Correct? X is base. 4x plus 1, x power 0, x power 1. And again, x power 0, x power 1. 4x plus 1. Here, 2 5 is 2x plus 5. Then 2x is equals to 4. X is equals to 2. Is wrong. Why? You are writing 5 square equals 25. Is it in decimal? No. In unknown number system, how can I write 5 square equals 25? ये गलत है. It is wrong. Yes or no? 5 square equals 25 is valid in decimal. But still, we are in unknown number system. Here, the step where we are converting to decimal. After converting to decimal, I can use decimal manipulation. But before converting to decimal, using decimal manipulations will be wrong. Will be wrong. So, whatever we have done is wrong. Then what is correct? Let us see. Square root of 4 1 is equals to 5. Assuming base is x. First calculate decimal equivalent of 4 1. 4x plus 1. Any doubt in that? Square root of 4x plus 1 is equals to 5 into x power 0 is 5. I am calculating decimal equivalent of 4 1 as a 4x plus 1. 4 1 means x power 0, x power 1, 4x plus 1 is equals to 5 into x power 0. I am calculating decimal equivalent of LHS and RHS. 5 into x power 0 is 5. Now I can write 4x plus 1 is equals to 5 square. Now I can write 4x plus 1 is equals to 25. Any doubt in that? No. We are in decimal. Now I can write 5 square equals 25. After converting to decimal, using decimal manipulations will be correct. 4x plus 1 equals 25. Then 4x equals to 24. X is equals to 6. X is equals to 6. Is it correct? Let us verify. Square root of 4 1 is in basics. Square root of, what is that here? 4 into 6 power 1 plus 1 into 6 power 0. The square root of 4 6 are 24 plus 1 into 6 power 0 is 1. So 25. What is this here? 5. That is LHS. What about RHS? 5 in base 6. 5 into 6 power 0. That is 5. So LHS is equals to RHS. Then it is valid. It is valid. The base we are mentioning 6 is valid. So people are answering, many have answered as 2. Please check. You are saying 2 means, right? You are doing the mistake which I mentioned last one. There is a possibility for doing that mistake. Not only here, in other also other examples also you may be doing such mistakes without observing whether it is converted to decimal or not. You may be using decimal manipulation. You can use decimal manipulations after converting to decimal. Before converting to decimal in unknown number system, I cannot use decimal manipulations. Yes. Next question. Find the base value which can satisfy this equation. Right. Same way we can proceed. Assume base is x. Then what we can get? Do we need to do this? Do we need to do this analysis? Can't we say directly? Yes. 11 6 is 66. It is decimal. It is decimal. Or if you are dividing 66 with 6, we are getting 11. Yes, it is correct. But let us go with procedure, whatever we have been following. X power 0, x power 1. Here x power 0, x power 0, x power 1. What is decimal equivalent of 6, 6? 6x plus 6. What is decimal equivalent of 6? 6 into 6, x power 0 is 6. And again, 1 decimal equivalent is x plus 1. Then 6x plus 6 is equals to 6 into x plus 1. 6x plus 6 is equals to 6x plus 6. Are we getting x equals 10? No. What is the x values can satisfy this equation? What are the x values which can satisfy this equation? Any value. Any value of x can satisfy this equation. When it is any value, what can be the base? Any base. It is not only 10. It is satisfying any value of x. If it is any value of x, I can say it is any base. I can say it is any base. Right? But in the number system, 6 must be a valid digit means x cannot be 6, x cannot be less than 6. Understand point correctly? Anyways, accepting, but in the given equation, if you are observing, the most digit used is 6. 6 will be a valid digit in base 7 and above. It cannot be base 6. It cannot be less than 6 also. Because in the given equation, we are using 6 also. 6 will be a valid digit from base 7 and above. 6 is a symbol which is valid in the number systems greater than or equals to 7 only. 6 is not a symbol in base 6. 6 is not a symbol in base less than 6. 6 will be a valid symbol from base 7 and above. So any base is correct which must be greater than or equals to 7. It can be 7. It can be greater than 7. Any base, but conditionally. What is that condition? Greater than or equals to 7. Why you are saying it is 7? In the given equation, the most digit is 6. That 6 will be a valid symbol from base 7 onwards only. So x possible value can be 7 and above. In the same, if I have a 8 by 8 equals to 1, 1, then any base which is greater than or equals to 9. Because 8 is a valid symbol from base 9 onwards only. So if I use 8 by 8 equals to 1, 1, if this is the equation, same possibilities we get any base which is greater than or equals to 9. As it is 6 by 6 equals to 1, 1. So we are getting that any value of x, so any base, but to validate it, so we go with the symbols. In this, 6 is a valid symbol from base 7 and above. That is the reason any base greater than or equals to 7. Right. Yes. Surya Sai greater than 6 is correct. Greater than 6 is also correct. Greater than or equals to 7 means greater than 6 only. We are using integers only. We don't have fractions. Because I cannot have that 0.5 symbol or 0.25 symbol. There won't be fractions in base. So if it is greater than 6 also is valid, which is greater than 6 means next integer is 7 only. When we are considering only integers, that's what I mentioned, Triveni. Greater than 6 is also correct. Greater than 6 means next number is what? Greater than 6. I'm not saying equal. Greater than 6. Greater than 6 means what? 7 and above. Let me take one more example. Find the base values which can satisfy this equation. Dinesh Roy, any value of x can satisfy the equation, which is indicating that any base. Yugasri, it will be equal, but it is not valid. Om Shri Krishna Karanam. Calculate decimal equivalent of LHS and RHS to validate that. Most of you are in right way of thinking. Just check it. Assuming base is x, then x power 0, x power 1, x power 2. Here x power 0, x power 1, x power 0, x power 1, x power minus 1. Then 3x square plus x plus 2 divided by 2x plus 0, decimal equivalent. X plus 3 plus x power minus 1. Then 3x square plus x plus 2 is equals to, multiplying with 2x. What we get here? 2x square, 2x into 3, 6x. 2x into x power minus 1 is 2. Then 3x square minus 2x square, x square, x minus 6x, it is 5x, is equals to 0. If I take x common, x minus 5 is equals to 0. X equals to 0 or 5. And again, 0 can't be the base. Why? Without using any symbol, how can I represent a number? What do you mean by 0 is the base, sir? Don't use any symbol. Then how can I convey a number? Impossible, right? 0 can't be the base. 5 is a valid base, sir. Verify with LHS and RHS decimal equivalent. 5 is a valid base. With respect to digits, it is valid. With respect to digits, it is valid. All the digits are lesser than 5. With respect to digits, it is valid. Vikas Singh, why are you getting x equals to 2? People are checking, some people are saying 4. That means 4 will be valid with respect to digits, but functionally, it is not valid. Functionality is important. Equation must be satisfying in that number system. Don't go with always symbols only. After getting x values, we are going to verify whether it is possible or valid or not. Yes. For today, let me wind up here. If you have any doubts, let me go with your doubts. If you don't have any doubts, you can leave the meeting. Right. One by one, let me address your doubts. Yes. Satvik, please unmute and talk. Satvik Behera.
Sir,
I'm not getting any voice from you.
sir, can you hear me now? Hello? Hello? Hello?
Satvik.
Yes, sir. Hello?
Yeah, tell me.
Sir, that you converted it to one a base equivalent 8. That one I couldn't understand. For
Which
that's
can
8
you
when
can you
20, 8 converted to 22 and that one, that problem, sir.
okay.
From 4 square to 4.
Please let me mention that whenever you have a doubt, please remember that frame number.
Okay, sir.
Please, that will be very easy.
This one, this one.
This one.
Yes, sir. Green column. From 16 to 4.
16 to 4. A is 2
That
2.
is 22 and 8 is 20.
It is
So
not
that
22. It is
how
not.
come
Listen. It is
2?
not 22.
Yes, sir.
2 2. A is what? Decimal equivalent.
Hexadecimal is 10.
10. 10. We need to convert to base 4. 4 to the 8. Remainder is 2.
Okay, sir.
Right?
Thank you. Yes, sir. Got it.
Right. Yogesh Kumar.
Hello, sir.
Yes.
Sir, I don't have any doubt, but it's a general doubt that you can convert the screen to white, sir.
What is that question?
Sir, you can convert the screen to white instead of black.
That I do. I
And
tried.
the the pen size also you can decrease, sir, because it's so.
Okay. It's like brushing, right?
because,
Okay.
Yes.
Okay.
That's only.
Okay. Right.
Thank you.
Naveen.
Yes, sir. Can you hear me?
Yeah, tell me.
Sir, in the beginning, I had a doubt about decimal to conversions. Can you give me a look at that? Uh, yes, sir. About just a minute. Yes, sir. The topic is decimal to any base.
Mhm.
Sir, in binary conversions, in the fractional part, we have used all the 319.68, for example, sir. Yeah, that's it. Sir, in binary conversion, we have all used 6875, but in octal, we have used only 0.67875 and 0.5. Why is that, sir?
Where is that?
In octal conversion, sir, binary to octal.
Binary to octal.
In binary octal, we have used only 0.6875 and 0.5. But where in
Please.
binary,
Come down. Are you
Okay, sir.
asking that decimal to octal or binary to octal?
No, I'm sorry, sir. Decimal to octal.
Decimal to octal here is there.
Yes, sir. Yes.
have considered both, right? 319 integer part,
Yes, sir, I
0.687
understood
fraction.
that. Sir. In a binary conversion, we have used all the units, I think 0.6875 like that, sir. Yeah. We have all the units 0.67875, 875, 75, and 5. Right, sir?
It is not like that. That is
I'm
becoming like that.
I'm unable to understand that, sir.
Yes,
Can you
yes.
explain it to me?
What is that?
The binary conversion, sir. Can you explain from the beginning?
This one you are asking?
Yes, sir. Yes, sir. The fractional part.
Fractional part. 0.6875
Yes, sir.
multiplied with 2. What we are getting?
Okay.
1.375.
1.375.
What is integer part in this? 1.
1.
What is fraction part remaining?
3.3375.
0.375.
Discard it. Okay, sir.
Right? What is discarding? 1 is integer part.
0.
Right?
Yes, sir.
Fraction part is 0.375 multiplied with 2. What we
Okay.
are getting? 0.75.
0.75. Okay.
Right? We are getting 0
Okay.
integer part.
Okay.
0.75.
Okay. Okay.
Remaining fraction part is what? 0.75.
Okay. So we have to multiply with the fractional part of the
Previous
before
result. Yes.
previous equation. Okay.
Yes. Yes.
That is the one, sir. That is the one.
Yes.
Thank you, sir.
Yeah. Right. Right.
In octal conversion, can you go to octal conversion? So the remainder is 5.5. Integral part is 5.5.
So integer part is 5.
Okay.
Remaining 0.5 is multiplied with
Okay.
8. Is resulting 4.0. Integer is 4.
Okay. Thank you, sir. That is my doubt. I have
Right.
clarified it. Thank you.
Very good. Thank you.
Can I leave the meeting, sir?
Yes. If you don't have any doubt.
That is the only doubt I have.
Okay.
All is very well and all is very clear, sir. Thank you.
Thank you. Thank you.
Hello, sir.
Yes, Pranit.
Sir, can you name some of the standard textbooks for digital?
Yeah.
Sir?
Yeah. I'll give you the list. I'll give you the
Okay.
list. Right. I'll give you soon. I'll
Okay.
announce in the class itself. I'll display in a slide all this. Right.
Okay. Tomorrow you will display, no, sir?
Yes. Yes.
Okay. Thank you, sir.
Right. Venkata Brahma Reddy.
Sir, in the last question, sir.
Yes.
Sir, less than 5 years is also base we have to take now, sir.
Is this one or next one?
Last one, sir.
Okay.
Here x equal to 5, it is base is valid now, sir.
X is 5 is valid.
Below 5, sir. Less than 5.
Why you want to take that below 5? Is it valid with respect to decimal equivalents? If I consider base 4, is it getting equal?
No.
Functionality is important.
Yeah, okay, sir.
Not only digits.
Okay, sir.
Right? Not only digits, it must be satisfying with respect to
Base.
right. Equation,
Yes.
functionality. Right? In base 4, if you are dividing these two, it must be giving this in base 4.
Okay, sir.
Then
Okay,
only
got
it
it,
is
sir.
valid. Right.
Okay. Thank you, sir.
Kashyap.
Yes, sir. Sir, I don't understand the second example of lower to higher conversion from base 3 to base 9.
Okay. Example you did not understand or everything?
No, just the second example I don't understand, sir.
Okay. I'll take that. Where
From
is
base
it?
3 to base 9.
Base 3 to base 9. Base 3 to base 9.
This one, sir.
This one.
No,
Where is it? Which
this
example?
one, sir. This one, sir.
This one?
Base 3 to base. Below,
Okay.
left below.
Okay. Then 0, 1 is one set.
Yes, sir.
For this, what is the decimal equivalent? 3 power 0, 3 power 1.
Yes, sir.
1. For 0, 1 again, 1. Or you can go with the list simply. Here. 0, 1 is a group 1. 0, 2 is a group 2. 1, 0 group 3. 1, 1 group is 4. 1, 2 is 5. 2, 0 is 6. 2, 1 is 7. 2, 2 is 7.
So could you please tell me how did you get this list? Is there any shortcut to remember?
No shortcut at all. Right. See, 0, 1, 2, 3, 4, 5, 6, 7, 8. In which number system? Base 9.
Yes,
So
nine.
base 3, what we get? 0 is obviously 2 zeros. Any doubt in that?
No, sir.
T square base. And n, that means n equals to 2.
Yes,
Each
sir.
symbol is represented using 2 digits. 1 is 1 only, right? In base 3 also. Then what should I write?
Yes, sir.
0, 1. 2 is 2 only. But I need to use 2 digits. 0, 2. 3,
1, 0.
Yes. Next
1,
1,
1,
1.
1.
1, 2, 2, 0, 2,
Yes.
1, 2, 2. That's it.
Okay, okay, sir. Understood.
Right? Understood?
Okay, sir. Thank you.
Thank you. Thank you.
I've got it.
Right. Very good.
Okay, sir.
Very good. Triveni. Triveni.
Yes, sir, in 16th frame.
Yeah, okay. 16th frame.
Why we take greater than 7 or greater than 6, sir? Why we don't take below 6 value?
What is the digits available in this equation? If I take base 6, 6 is valid in base 6. Will it be valid 6 in base 6? In base 6, what is the valid symbols? 0 to 5.
Yes,
But
yes.
already 6 is used here.
Hmm.
How can I use base 6 if I use 6 already?
Okay, sir.
Right? Understood?
Yes, yes, sir.
Right, right. Any more? Kashyap. Once again.
Sir.
Sir, tell me.
Yes, sir. No, sir. I got clarify.
Okay, right. Sanjeev.
Audible.
Some disturbance is there. Not audible, Sanjeev.
Sir, now I am audible, sir.
Yes, yes, yes.
So I have a doubt that in decimal any base in the fraction part we have multiplied the base binary, sir.
Okay.
But in that model B to B power n to B model, in the
Okay.
fraction we have did division, sir. Is that rule or?
I did not divide each and every digit. I have done that. It is each
10
and
F,
every
sir.
each and every digit I have done. Not only one. I am not doing that entire number. Symbol by symbol. Conversion is symbol by symbol.
Oh, okay, sir. Okay, sir. 10F, sir. 10F.
Okay. 10F. Okay. Okay. I'm doing that symbol by symbol, right?
Symbol by
I'm
symbol,
taking-
we have to.
Yeah, yeah.
Okay, sir.
Direct conversion.
Okay, sir. Okay, sir. Thank you, sir.
Thank you. Thank you. Sajjan Singh. Sajjan Singh.
Hello. Yes, sir.
Yeah, tell me.
Sir, if we get only single value of x, then should we cross check it or not?
Better to verify.
Verify.
Better to verify.
Okay, sir.
Okay.
Thank you.
Srinath.
Hello, sir.
Yes.
Sir, in the same page, sir.
Okay.
If the n value is 3 or 4, if we kept 3 power of 3 or 4, how to do, sir, answer?
Once again, n value is instead of 2, it is 3.
Either, yes, sir, 3 or 4.
Okay. Same thing, whatever we have done in octal to binary and hexadecimal to binary.
By this process, we can't do that, sir.
You can do what is there in that.
If we
If
kept
there's-
3,
See,
what to do?
for example, octal is there, 7 is there. We want to get binary. We don't know that 7 is 111. What do we do? 2, 3, 2, 3 remainder is 1, 2 1 remainder is 1. What do we get here? 111. You are getting right.
No, sir. Sir, you did the first value of 6 with LCM 3, sir. You get 2 and 0. You kept the answer here 2 0, sir.
Yes, sir.
If we have to find out 3 power of 3, sir, do we need to add another 0 in front of 0? Is that okay?
For this 6 you are saying?
Yes, sir.
Yeah, 0 2 0.
If 4, sir, 3 power of 4?
0 0 2 0.
Okay, sir.
Right. Right. Santosh Singh.
Hello. Sir,
Yes.
in the same slide, sir.
Yes.
First, you said to convert the radix 9 to radix 10, no, sir.
Radix 9 to radix.
Base, that is decimal 2, again radix 3, no, sir.
Okay.
If we convert, we are getting the different value, sir.
The value will be, fraction will be, that is
Yes, sir.
never ending.
Yes, sir, never ending, sir. How we have to round off?
Better to go with this. In
This
this
one
case.
only, sir.
If there is a question, there will be correct answer.
Okay, sir.
When we are framing a question or examiner is framing a question, there must be an answer. They won't give such questions. No need to worry about it.
Okay, sir. Thank you.
Right. Yugasri. Yugasri. Vignesh.
Sir,
Yeah, Vignesh is talking. Yes, tell me.
sir, can you hear us, sir?
Yes, tell me.
Sir, that b power n to b is a little bit confusing, sir.
Why are you getting confusion? Octal to binary, are you comfortable?
Yes, sir.
Hexadecimal to binary, you are comfortable?
Yes, sir.
How you are comfortable in that? You are remembering? Am I right?
Sir,
You are trying to remember that. You are not finding any logic there. You have remembered, it was comfortable. Now you are trying to understand the logic, you are finding a difficulty, right?
Yes, sir.
Right? Try to understand the logic. B power n to b. Each and every symbol should be represented using n digits in base b. That's
Yes,
it.
sir.
That's it. That is the logic we have used in octal to binary, hexadecimal to binary also.
Okay, sir.
Right? Understand the logic. Don't remember. Octal to binary also, you don't need to remember.
Okay,
Right?
sir.
Right.
Okay, sir.
Right.
Thank you, sir.
Right.
Sir,
Yes, Yuvasri.
sir, 66 by 6 is equals to 11. LHS is not equal to RHS is not coming, sir, for me.
Which base?
Can you explain it? Which base 7 greater than or equal to 7 base you told us, sir.
Oh, yes.
I
So
kept 7 base, sir, but it is getting 8, sir.
6 divided by 6 is equals to 1, 1. Which number system you are using? 7. Right? 7 power 0, 7 power 1. 7 power 0, 7 power 0, 7 power 1. What is the value of this?
7 is 42.
7s are 42,
42
plus 6.
plus
48.
8.
What is the decimal equivalent of 6? 6 into 7 power 6.
6.
So what is this here now? 8. LHS decimal equivalent is what? 8. What about RHS? 1 1 7 power 0 7 power 1. 7 1 is 7 plus 1 into is 1. What is that here? 8. LHS decimal equivalent is 8. RHS decimal equivalent is also 8.
Okay, okay.
Right?
Okay, sir. Now I get clarity.
Okay, very good. Any more doubts? Rohit.
Hello, sir.
Yes.
Good evening, sir.
Good evening. Very good evening. Tell me.
Sir, 3F, sir.
3F. Very good. 3F. Okay.
Sir, in R raised to minus M, what, sir, that?
When we have, for example, 101.01, what we write? 2 power 0, 2 power 1, 2 power
2 power 2.
2.
1.
Here 2 power minus 1, 2 power minus 2.
Yes, sir.
If we have that m digits, we have it, we get 2 power minus m. That's it.
Yes, sir. Okay, sir. Right. Thank you, sir. Sir, and in equation, sir.
Which one?
Last, sir. Sir, in the equations, if they given square like that thing, sir, how to calculate, sir?
That's what we go
square
to
or cube,
decimal.
cubic
Decimal.
equations.
Right. We can do that decimal.
Sir.
Then we can.
Can you explain, sir, a little bit?
I'll give you that examples later.
Okay, sir. Thank you.
Right.
Thank you, sir.
Right. Any more doubts? Okay. See you tomorrow. If you don't have any doubts.